Hi, so let's start our seminar. Um, so the plan of our seminar will be about this article. Oh, I'm sorry. Yeah, so we will talk about we'll tell you about DeepSeek Math. So this article, we will, I think, say detailed about group relative policy optimization. And we compare it with DPO, direct policy optimization. So, and say some examples in practice. So, but we will not have a great practice example because so to train language model, even so small language model like 1 billion parameter, only 1 billion. So it's really hard work, and we need computer sources, and I don't have it. So that's why I just provide you code, and I show that it works, but it have some errors, and it falls down because we have not enough memory. So let's begin with this paper. So and this paper introduce DeepSeek Math, specialized language model designed to excel at mathematical reasoning. So and we will focus on a group relative policy optimization and its differences from other reinforcement learning methods. So, a small overview of DeepSeek Math. So it is a 7B parameter language model that builds on a DeepSeek coder base version 1.5. Further trained on 120 billion math-related tokens from Common Crawl. So, and what it achieves? It achieves some great scores. So more than 50% accuracy on the math benchmark, completion level problems. So more than 60% when using self-consistency. So some 76 samples, and outperforms Minerva. It's I don't see this, but okay, it's outperforms Minerva 540 billion parameter, a significantly larger model, so really larger. So and most open source models. So and how it can achieve these results? So the key contributions which what we have. So what authors have done. So it's a high quality math data selection from Common Crawl, more than 7 times larger than Minerva's dataset. So we have more high quality math data. So the first contribution. So the second, group relative policy optimization. So it's an efficient reinforcement learning method that improves the mathematical reasoning while reducing memory usage. So DeepSeek will use the same group relative policy optimization for a DeepSeek model like R1. So it's one of the great reasoning models, and I use it too. So and it works great. So sometimes better than GPT-4o, so or something else models. So Sonnet, Cloud Sonnet 3.5. So DeepSeek can solve many code problems and can solve it really successfully. So, but sometimes even so. Anyway, I sometimes have to do all work by myself. So, and so the last contribution of achieving such results in this paper, so it's strong multilingual performance. So in English and in Chinese math benchmarks. So I think it's great contribution because we have the same math in English and in Chinese. So we have a multilingual model, and we excel the size of the data set. We excel the diversity of data. So I think it's the key contribution. So let's discuss something that's introduction. Okay, so contributions, math pretending scale. Okay, well, what we need. So I think I can tell you about core methodology. So, and first of it, of course, it's data collection and pre-training. So we have here the data pipeline. Data pipeline. So I don't see it, but I really remember how it works. So I couldn't find it just pipeline, so but it doesn't matter. So first, they use iterative filtering with a fast text classifier. Maybe I can search here. Maybe I really remember. So it's fast text. Oh, here. Okay. So we see it. So it's in intro. Okay. Um. So uh. So they use iterative filtering with a fast text classifier. Yes, to extract math-related content from a common crawl, and their final dataset. So it's have 120 billion math tokens, so including math web pages, code, and natural language data. So and they ensures that benchmark questions are not leaked into training. So it's, of course, it's important. So model training, if about model training, so they start from a DeepSeek coder base. They initialize, yes, with the version 1.5 7D. So pretend on code, yes, and they have a mixed continual training. So 56, I don't see this. Okay, I don't see these numbers about the data set. But okay, more than 50% of the training, it's a DeepSeek math corpus, math web data. 4% it's algebraic stack about the math code. About 10% it's archive papers. 20% is GitHub code, and 10% is general web text. So and then they use fine tuning, so self fine tunings. They use 700 more than 700,000 instructions examples with chain of thought reasoning, program thought solutions, just like a Python code, yes, and tool integrated reasoning, so some external calculations. So let's move to the math pre-training. We have a great here we can see the common crawl, yes, and some iterative pipeline of the some of the retrieving the data. So from the math from a common crawl, yes, and here so you here we have some corpuses, math pile, open web math, proof pile, and etc. So and training setting, yes. So as you can see, we have some Adam V optimizer. It's one of the greatest optimizer now, but sometimes it's really we have some it's you have to have a lot of memory for this. So yes. So and here it is. Yes. So here you can see the final benchmarks. Yes, it's results performance of the DeepSeek Math Corpus. Yes, so it's great performance. Well, evaluation result. Yes, so they made a great model. I'm sorry. Oh, great. So I have to find my APK. Nice. Not nice, of course. Not nice, but okay, let's move to another. So it's our seminar. So yes, this is the multilingual model. Okay, but I think we can move to not supervised. I think here reinforcement learning. So it's I think this is the fourth topic. The fourth topic of this article is one of the most vital topic. So and here we see the detailed definition of group relative policy optimization, GRPO. So and GRPO is a variant of PPO, proximal policy optimization. So and it designed it designed to remove the critic model one point because the critic model used in PPO for value estimation. The second point, estimate baselines from group rewards, reduce memory usage. It's vital. It's vital for our computational resources. So, and the third point, the GRPO, it uses relative rewards within a group, like a batch of responses, rather than absolute values. So, and how GRPO works? So, first of all, we have some reward computation and baseline. Yes, so I think we can see. Okay, okay. So, uh, great, great scheme. So, yes. So for each question, we sample a group G of n answers. For example, n is 64. Yes, we compute a binary or a scalar reward for each answer. Yes, here. Um, for example, correct one, incorrect zero, or graded partial. It doesn't matter. So and we derive a group baseline by a, like mean of these rewards. Yes, and we define a relative reward um, for each sample, and then we have the policy update. So from this, yes. Uh, so we maximize the expected advantage weighted likelihood um, uh, by Kullback-Leibler distance. So and we maximize it, and sometimes we can use optional clipping as in PPO, but Kullback-Leibler in PPO we use here, but we use the maximize the expected advantage weighted likelihood on the from reference model and from the relative reward for each sample. So after the group computation. And in policy updation, uh, there are no separate value heads. So all advantage estimates come from the group statistics. So it's vital. And we can optionally apply the PPO style clipping, as I said, yes. Uh, but it's for just in stabilization, the training. As you can see, so they have a Kullback level penalty. Yes, so this maximization of it. So it is the loss hour, and here the iterative group policy optimization algorithm. So as you can see, we have initial policy, some hyperparameters, reference model. We sample our batch, update old policy. Yes, then we sample group outputs, rich questions, compute rewards, compute it's a advantage estimation, like relative reward. Yes, and update the policy by maximizing the GRPO objective. So, okay, this is the short, I think, understanding of GRPO, and so, but the differences, the key differences between GRPO and standard PPO, first of all, it's a critic removal. So PPO uses a learned value network, or value model, to predict values, doubling parameter count, of course, yes. So GRPO uses a group mean reward, so it's here, by dropping the value model and its equations. And of course, as a baseline, it's group mean reward is a baseline. So no extra network. And of course, this is why we have the memory efficiency. Yes. So as I said, we drop this model. So and we save about 50% of GPU memory. So it's great. Of course, the sample efficiency. So we have two because grouping correlated responses. So we got more stable baseline estimates. So, and sometimes, and overall, it's simpler. So GRPO much more simpler than PPO, as you can see. So this is the some fast summary about GRPO, grouped relative policy optimization, and so about the article, some results, some the overview. This model, DeepSeek Math, it demonstrates that specialized pre-training plus an efficient reinforcement learning algorithm, so group relative policy optimization, can significantly enhance mathematical and quant reasoning in complex 7B model. By removing the critic and leveraging group-based baselines, yes, this one and this one. So group relative policy optimization this method achieves great performance compared to PPO. And of course, with really lower memory costs. And one question after this article, could we make the same way for a large language models? Not for a code, DeepSeek Math, for example, yes, or math models, code models, or for the large language model with all, which we can pre-train on all these math corpuses, yes, data, and even more, like Wikipedia, some articles, etc. So this is why DeepSeek R1 or version 1.5, so it's great. It works great. So this was the article. If you have some questions, so you can ask me now. So
You were talking about the leveraging the groups for DeepSeek architecture, and by removing the value function. And I wanted to ask you, like, how do you determine the group size in GRPO, and how does it affect the variance and bias of the like group relative advantage estimator?
You mean biases in rewards?
Uh, yeah, for example, in reward, like biases and variance, because I like from what I understand, if we remove the value model, of course, we would have like the model itself would be very lightweight, but at the same time, I think it would increase the bias if I'm not wrong.
I think yes, a bit, but so I can find the group optimization here, and we will see. Oh, here's a clipping. A second, please. Um, as I remember, so the group baseline is the mean of the all reward functions, but the relative reward for each sample is like the difference between just a reward minus mean result. So this is group baseline. And this is the new relative reward. So I just try to find this formula. Oh, here it is. Here it is. So uh, we normalize. So to set the advantages, we normalize by the mean and standard deviation, and I think by normalization, we uh, cancel these biases. And of course, by normalizing, we stable our distribution of rewards. So I think by normalized, of course, we will have some biases, but of course, it can smooth it, I think, a bit. So smooth it, and as a result, the normalized reward uh, works will work so great.
No, I meant like, for example, in GRPO, group size refers to the number of responses that the model generates for one prompt, for example, or for a question during the training. And then, as far as I remember, these responses are evaluated together as a group. And my question was like, how do we determine the group size, like the optimal group size? For example, if the group size is 8, the model should produce 8 different answers to the same question. And then we use these 8 answers to calculate the group-based advantage for the policy optimization. So I just don't quite understand how this group size is determined. Is it like a hyperparameter, or is it a parameter that is learned during the training, or like something else?
Ah, I got it. So if we use only one example for GRPO, yes, so then we have zero standard deviations and biases. Am I right?
Basically, yes. So for like, of course, we will have different type of performance for different number of responses for the same question. So
Mm-hmm.
during training, how is the number of like appropriate number of responses determined? Do we like just do some hyperparameter tuning before the training is like starting, or is it a like parameter which is learned during the training itself, or something else?
Okay, okay, yeah, I got it. So, yeah, so great question. So it's similar to the batch normalization method, yes. So for example, I just for a reminder, just a small reminder. So in the batch normalization layer, so we have the learnable parameters, and then we apply these parameters to inference. But GRPO doesn't work in in inference. So we use this method only in training. So in training, we have a lot of examples and we have a lot of corpuses of text and so a lot of just I think prompts, yes, for learn. And here the methods just DPO, PPO, and GRPO, all of them we use in training our model and to align. So it's one of the part of alignment. Alignment is the process of to increase the performance of the model and increase the I think to make model more human-like. I think a bit. So GRPO works on and all of these methods, alignment method, they works not in inference. I think a bit we can use DPO in inference, yes, but we talk about GRPO and PPO. So this method we use on the training, and then we have in training so a lot of models, and so we don't have some biases like standard deviation like 0.
Okay.
Okay. So maybe some more questions. Well, let's see the code. So I will show you my RAM. So it's full. That's all. That's why. That's why I couldn't show you the example how we trained the model. Yes, but here I just want to show you code. Yes, in a computational of GRPO implementation and DPO implementation, and the differences in a loss function. So first of all, we have GRPO implementation, and here we sample a group of G outputs in a per prompt in a single batch. Yes, then we compute a scalar rewards. We compute the baseline group. Yes, then we make the advantages, as you can see in the formula in our article. Yes, and we have no value network. So as you can see, so we have some initializer method. Yes, generate group. So we have the batch encoding, just input IDs, attention masks. Oh, that's pretty so pretty base methods. But we generate group samples from a tokenizer from all our samples. We just generate this text. So we compute, then we have, so it's group samples, great, we can compute the rewards. So based on our prompts. So we, it's of course it's not really great reward function, but in a just we just scoring the returns tensor rewards in shape. Yes, from so here we have the line of prompts. Yes, and we have our rewards. Yes, so and reward for each prompt, each group samples. Yes, it's like the answers. It's not scoring. We score just it's a dummy score. But for example, just we have a something scoring method, something great from a DeepSeek. So I don't know the DeepSeek scoring method. Don't implement. So, but of course, nothing special. We score prompts and answers, yes, by this method, and we have our rewards. So great, we have our rewards. So then we have our inputs as compute log prompts, log probabilities. So we here we compute by the logits model. Yes, we have some shifts, but it's okay. Okay, so and the main part, we got the losses, token losses, yes, and then we compute the logit probabilities, so log probabilities, by this sum of all our tokens. And train step, it's the main part when we generate all our all our samples or based on our prompts. Yes. Then we got our answers. Yes. So we got our outputs. Then we compute our rewards for each prompt for each group. Here our baseline. So as you can see in a formula, yes, we just compute the mean of this reward. Then we make the advantages. So for all in all metrics, so it's a matrices. So here shapes of all these matrices. Yes, so it's rewards minus baseline. So and here we compute log probabilities by our method and compute our ratio. So it's an old policy. And PPO, this is the clipping. Clipping, we can clamp our ratio by some epsilon or some ratio. That's all. Yes, so we clipped just for stabilize training process. That's all. So at the end we optimize our make our zero gradation in optimizer and make our backward and optimizer steps. That's all. So especially the GRPO trainer, here we only in two functions. For example, this computer rewards, yes, by the our score. We don't know the score, but we can just imagine that we have something method, yes, of it. And training step here for computing rewards, make a baseline. We compute reward for all our prompts for our group. Yes, we sample, of course, we sample, generate the group. Yes, and then we have our advantages. That's all. So that's the core of GRPO. So direct preference optimization, as you remember, so we just choose the parameters, choose the great answer of the model, and then we have the loss function, which maybe I can show you DPO direct preference optimization, maybe here. Okay, yes, maximum likelihood. Oh, it's not really great. Oh, okay. I saw the great the better. Oh, yeah. So yes. So because for me this image is better for understanding. So for example, you have just for reminder about the DPO. Yes, you have two prompts. So this first prompt is chosen, the another prompt is rejected. Yes, so how we train language model. Yes, in a trained language model, yes, in the training process, we have two scores of the each prompt for chosen and rejected. Then we compute the reward policy. We divide the chosen score by the rejected score, and then we just add this reward policy in a loss function. That's all. So reward policy in the here we divide it by the reward reference. What is the reward reference? We have the frozen language model, which is great language model. I don't know, for example, the big language model. Yes, this language model to generate the chosen score and the rejected score too for each prompt. Yes, from the chosen, I mean this is the answer. Yes, the prompt plus the chosen answer prompt is rejected answer. So we choose the score, then we the compute the same way as a reward policy, reward reference chosen. We divide chosen by rejected and we add it in a loss. That's all. So and by this loss we updated the weights of the trained language model. So and this way we can train the language model, for example, small language model, answer the prompt for the chosen for a great answer. Yes, this is the green answer as frozen language model, which can be a large language model. So this is the key point. So I really hope so you got it. And that's all. So that's we have a model, we have a reference model, we have a tokenizer, optimizer. So beta, it's just the hyperparameter. Yes. So and we compute log prompts. Something similar. Yes, we have output of our model and we compute the label size. We have just multiply output from loss by the labeling. Labeling is just a sequence length. So and chain step. Yes, that's all. We have our prompt. We have our chosen. Chosen prompt and rejected prompt. So no, not chosen rejected. I mean this is the answers. Yes, so we have prompts and we have answers. So we tokenize it. Yes, then we compute our log probabilities. Yes, by our model. Then we compute the log probabilities by the reference model, and make the same for rejected part. Yes, so from our model, which we train, and the reference model, and then we have so pretty simple loss function. Yes, just log probabilities by the chosen and by the our model and reference model and rejected. That's all. And then we just make the mean. So we just compute the mean of this log sigmoid. That's all. So it's I I want I wanted to show you in a computationally in a code the differences between GRPO and DPO. So I don't want to implement the DPO because it's a bit harder. So here we can see the key differences between GRPO and DPO. So, and here the example. So I just wanted to make the to got the one small llama model 1B, and I really hoped I hoped that it but I got this situation in my memory. So but by the way, I just wanted to make the model. So download the model and the parameters. Work in a float 16. Float 16. It's not really great to train the model in a float 16. Better will be float 32, but float 32, it's we have twice. We have to have twice more, twice times more memory for a float 32. But and that's why I tried to use a float 16. So. And here I had the class of GRPO Lite, so with the same formulas and some logs of the GRPO baseline advantages and rewards. Yes, and I got the DPO with the same margin and DPO loss. Yes, and we have here the GRPO loss, and I wanted to compute some prompts. Yes, for example, some math prompts. Yes, just only two by the Atom. Yes, and I just wanted to compare the um, losses of the and parameters of these two methods. So, but so I got the device distance invalid. Great. So, by the way, I wanted to show this example, and so to show you how we can compute all these methods. So let's move to the last practice. So here we have something new. We have some quantization, LoRa, and self fine-tuning, but and here I really have to have some APK. Let's try to got it. Sign in. Okay, from Google, for example, this one. Continue. Oh, nice. Academic. 5 seconds, please. I just got the APK. Oh, nice. Hooray. I really hope you trained. So, yes. So here we want to just got the model, then got the quantization model, get the LoRa and self fine-tuning. So we got the model on the T-Tech, T-Lite. It's from a Tinkoff bank. If you, 1 second, I will show you. Yeah, here it is. So T-Lite or T-Tech company is a Tinkoff official company in a Hugging Face. So as you can see, they have here a lot of collections, yes, of some models, some benchmarks. So and we used, or it falls down, out of memory error. Okay, great. Okay, out of memory, nice. The same error. So by the way, so we use we wanted to use this model. Yes, got the tokenizer. So and download the model. Great. So we got it. Thank you for your face. So and as you can see, so we have some Quen layers. Yes, because the T-Lite model based on the Quen model. So by the embedding, some Quen decoder layer, Quen MLP, etc. So, and so as you can see, we have a usage example. For example, what is UTNOS? Yes, and as you can see, so the answer is great a bit. So something, the word UTNOS means refusal in Japanese culture. Yes, so it comes from the verb yutsu, which means to refuse or to reject. Yes, the suffix nas is added, etc. So as you can see, it works great. So and especially for me, it's great. So Delight IT1, not Pro, Delight IT, this one. So about the parameters, it's really light. So it works great for prompts, as you can see. Yes, great answer. Yes, we have some problems with the context because, as you can see, it stops. It stopped in the middle of the thought. Yes, but we got really great and understandable answer of this model. So and as you can see, it weighs a bit, just 15 gigabytes. So a bit. So yes, and here how we can apply the LoRa from this model. So first of all, we have a LoRa config. Here as we can see here how we can use this adapters, not only LoRa, so low rank adaptation, but especially some other PEFT methods. Yes, because there's some mixture of experts. So low rank connector product, yes, etc. But we wanted to use the simple one. So the LoRa. Yes, and target models is our I'm sorry, query and value projection. Yes, this is what we really want to reuse. Yes, and I think that's all. We have some hyperparameters, and we use our get beft model, and we can print the trainable parameters. So all parameters is more than 7 billion. So it's a trainable, but all of this trainable only less than a 1%, less than a 0.5%. So only 2 million. So this is the structure of our model, our PEP model new. Yes, and we have our self fine-tuning dataset. We wanted to use Databricks, 15,000 samples. Yes, for a split training split. Yes, and we downloaded it. Yes, great. So we have some instructions, we have some context, response, category, etc. And we train our model by this loss. So this loss, it's a really simple cross entropy loss. Yes, by the answers and input data. Yes, and here we use all previous generated tokens here. Yes, we of course we use our probability. Yes, of the new tokens true token position. Yes, based on the input data and all previous generated token before our position. So yes, great. We have our trainer, we have our self-config, but out of memory error. Thank you so much, Google Colab. Yes, maybe we want to relogin, to force relogin. I don't know. Maybe it will work. I don't really know. Oh, excuse me. Okay. No. So I'm very sorry, but we don't have computational resources, so large computational resources for training large language model, and but so you can trust me. So everything will work. So if you have, I think so in I don't know, just you have maybe on your PC. Yes, so you just can try to train these models, train to try to the GRPO and DPO methods, yes, and some these LoRa self fine-tuning. So this is the end of our seminar. We um, got the detailed definition of group relative policy optimization based on the DeepSeek math model and the article. So we so the article, so real detailed, and so some formulas. Then we moved to the practice mode, and we tried to compare the GRPO and DPO, and we saw how it the differences in a loss function in a GRPO and DPO. Yes, so and we tried to compare it in a training model in a prompts in correct or just rejected and accept answers. Yes, so then we moved to a small example of how we can download the large language model. It's just about quantized. How we can use the LoRa config, how we can download LoRa and to make the low rank adapter mod for our model, which we download from the Hugging Face, and then we download the self-fine-tuning dataset, yes, the corpus of it dataset, corpus of text, and then we tried to train this LoRa model by our API. So, but anyway, we don't have so much memory, yes, for full training process. So excuse me, but this is our seminar was about, and really thank you for such seminar for this day, for this practice. And if you have some questions, so you can ask me now. So 3, 2, 1.
We have a class next week.
I think yes. I think yes now today. But if something will change, of course I will warn you in advance in the chat.
And about all the homeworks, would it be possible to forward them to our group chat? Because we're not sure which ones to do, which contests to do in the channel.
Okay, so we have. Okay, I just stop share. I can forward you this task. So the deadline is 11th May. So I know. 1 second, please. Here it is. So the first link, yes, it's the homework. So it's the two Jupyter notebooks. So the main is the main notebook. Yes, so I can just open it and share the screen. Okay, so here's the main notebook. Here it is, yes, and here you have to do this main notebook, and this notebook you have to send here. Yes, here your email, your first name, your last name, your first name, yes, some. This is the iPad notebook. Here, this is the rate of the homework. So, and some, I don't know, your opinion about this notebook. So you can debug, you can use the debug notebook for debugging your DeepQ network. So, but if you want, so yes, close. So this is your homework. Some words about it. Yeah, I really warn you that the authors of this notebook, so they didn't manage dependencies well. This is why you will have some errors and some bugs in Jupyter notebook. And this is the, I think, the craziest part of this homework. It's just to stable your environment of Google Colab. For example, all your homework, I tried to do it by myself, because I really want to have an opportunity to answer your questions after homework. So, and for example, just this is your homework, yes, and I had to rewrite this part. I mean this part, so I can delete it. So, and then I add this one cell, yes, and this one. So for stable work of this notebook. So because there are a lot of problems, and even after this, I had some attribute error, like model numpy has no attribute bool 8 because they use the numpy first, and this is the craziest style, and I don't how to fix them. So I did this notebook yesterday, so but I did only just about a half of the work. So this is your homework, and I really hope that you will done it. So you will do it, and everything will be okay. So, but I really hope you, and I wish you good luck with it. So, start the homework in advance.
How much marks is the homework worth, like in total for the grade?
I don't exactly know, but about 25%, because we have four homework. I don't exactly know. I'm sorry.
We have 4 homeworks.
Yes, you have 4 homeworks. I can show you. 1 second, please. So you have word vectors. This is the assignment for a word to back. Attention. I don't know why it's in Russian, but maybe something. Text classification for BERT, and classic text classifier for BERT, and now DeepCon network. It's
Sorry, could I ask, the before for homework is on index context, right? The before for homework is on index context, right?
Yes.
Okay, so and this homework deadline is 17 May, right?
Maybe I don't remember.
Yeah, but we talked with the Giraffe-ai guys, and they were like, "We'll send you the homework when you have to do it." I don't think anyone did the homework right now, any of them. We are way past the deadline.
No. So, okay, so maybe we can tag the Giraffe-ai and asked about the homework. So, okay, I will do it. Well, if you have some question, so you can ask me.
About the exam, like, will you be our examiner? Like, as far as I
Yes.
remember, you said.
Yes, I will be the examiner, and the exam will be online.
Oh, it will be online.
Yes, on a 29th May, if I don't mistake. I just see. So we had 1 second. No. 5 June. The 5th June. Maybe we will move this day, because I have exams too at this date, so it will be not the 5 June, and maybe 6 June or something else. So, but it will be online. It's this 100%.
Okay, thank you.
Okay. So, thank you very much for this seminar. So, for attending this seminar. Have a nice day. Goodbye.
Thank you. Have a nice day.